Acid-base titration. Titration is a procedure to determine the concentration of a solution. So let's start with the acidic solution. So here in conical flask we have some hydrochloric acid solution and we know the volume of HCl. Let's start with 20 ml. And we don't know the concentration of HCl. We can find out the concentration of HCl by doing a titration. In acid-base titration, we need an indicator that can indicate the completion of reaction because various indicators are available which can change their color with change in pH. So for example, if we have acid solution, that is HCl, and we add few drops of an indicator that will indicate the pH of HCl, for example. So let's add few drops of phenolphthalein that acts as an acid-base indicator which shows colorless solution when the solution is acidic, and it turns to pink color when the solution turns to basic solution. So in this conical flask we have a solution of an acid, that is HCl, and few drops of an indicator, and this solution is initially colorless. Up here in the burette we need to add a standard solution. For example, we need a base that can neutralize this acid. If we are taking the strong acid, we need a strong base to neutralize. So we need to take the standard solution of sodium hydroxide. So let's say we have poured a sodium hydroxide solution to the burette having concentration of 0.100 molar. Now we are ready to start the titration, and we allow the sodium hydroxide to drip into the HCl solution, drop wise into the HCl, and having the few drops of indicator, and we need to swirl the flask slowly so that the sodium hydroxide that is dropping to the conical flask must dissolve uniformly to the HCl solution. So in this way we are doing an acid-base reaction in which HCl is neutralized by a base, that is sodium hydroxide or the standard base, to produce sodium chloride and water. So in this reaction we are using the process of acid-base neutralization. That's because the acid and alkali solutions are being neutralized to produce salt that having a pH which is around 7. So slowly we have added a certain amount of sodium hydroxide to the HCl solution so that the volume of the HCl is increasing to a level so that the solution turns light pink, and it stays light pink. That means all of the acid have been neutralized by the base. As the indicator turns to pink in color when it's a slightly basic solution, so the color of the solution in conical flask is light pink. That is due to the presence of slight excess of the sodium hydroxide within the solution that turn the color of the indicator, that is phenolphthalein, into pink color. So this condition indicates that all the acid is being neutralized by the sodium hydroxide. So the light pink color is called the endpoint of the acid-base titration. So we have two volume marks on the burette, that is V1 when we have started the dropping of sodium hydroxide into the conical flask, and we have volume V2, that is for endpoint when the color of the HCl solution turns to pink. So here we need to calculate the volume of the base that has been used. So let's start. We have started from V1 and we reached to a point V2, that is the endpoint. So this is the volume of base that we have used during the titration. So there is a change in volume. So for example, we have used the volume that is 48.6 ml to completely neutralize the acid within the conical flask. Now using this volume we can calculate the concentration of HCl. So how we can do that? So let's start with concentration of sodium hydroxide. So we have started with concentration of sodium hydroxide that was 0.100 molar. So here molarity is actually equal to 0.100 moles per liter. So our goal is to find out how many moles of the base that have been used to neutralize the acid that was present. So as we have the volume of the sodium hydroxide that is in liters, so we have to convert the volume that of the sodium hydroxide that has been used to neutralize the HCl into liter. So how much volume we have used? 48.6 milliliter. That must be equal to 0.0486 liter. So we need to divide this volume. So here 0.100 is actually equal to x over 0.0486. So here x are the number of moles. So in this way we can calculate the number of moles of sodium hydroxide that is the value of x is equal to 0.00486 mole of sodium hydroxide that have been used in our titration. So now look at the balanced equation. There is one here and again one for sodium hydroxide. It means 1 moles of HCl must react with 1 moles of sodium hydroxide to produce 1 mole of sodium chloride and 1 mole of water. It means that acid is being neutralized by sodium hydroxide through 1:1 ratio. And the equivalence point is the point where is just enough of the standard solution have been added to completely react to its solution of which it have been titrated. And at this equivalence point, all the acid have been neutralized. It means it has been completely reacted. So this number of moles have been used to neutralize the HCl at equivalence point. That means, so therefore I can go ahead and write that I must have 0.00486 mole of HCl in the flask before we have started the titration. It is because we knew that at equivalence point there is 1:1 ratio that is represented from the balanced chemical equation. So let's remember our goal is to find the concentration of HCl, that is molarity. So the concentration is actually moles per liter. And we know that the number of moles of HCl that has been present within the flask, and we also started the volume of HCl that was 20 milliliter. So at first we need to convert 20 milliliter into liters. So let's see what is the concentration of HCl. So how many moles we have? 0.00486 moles over liters of solution. So the volume should be written in liter, that is 0.0020 liter. So here we have to divide the volume of the solution, so it must give the concentration of HCl. So we get 0.243 molar. So we have calculated the original concentration of HCl. So there is a shortcut way to solve this problem. So we need to consider a formula, that is M1V1 over N1 must be equal to M2V2 over N2. So here M1 is the molarity of sodium hydroxide, V1 is the volume of sodium hydroxide, and N1 is the number of moles that are from the stoichiometric balanced equation. So M2, V2 and N2 are the values for acid. So here if we know the So for our example, as we have used acid in the conical flask, so we must use 1 for the acid, because we need to calculate the molarity of acid, and the second terms will be for base. So here we know the volume of the acid we started with, and we need to calculate the molarity of the acid, that is M1, and we already know the volume of the acid, that is V1. As the chemical equation is 1:1, so the N1 and N2 are equal to 1. So we have used the standard sodium hydroxide solution having molarity of 0.1 molar. The volume of the sodium hydroxide that has been used was 48.6 ml, and the number of moles are 1, whereas number of moles of the base was denoted as N2, so it is 1 into the volume of the acid that we have started is 20 ml. So here we don't have need to convert the volume ml into liter, because we have to divide volume with volume, so we don't have the unit of volume in it. In this simple way, or the shortcut way, we can easily calculate the molarity of the acid that has been used for the acid-base titration. So in this way we can easily calculate the concentration of acid, that is unknown concentration. Now let's discuss a titration problem. So here we have a titration problem which is asking a question that in a titration 27.4 ml of a 0.0154 molar solution of barium hydroxide is needed to neutralize 20.0 ml of HCl. What was the concentration of acid solution? So we have 20.0 milliliter of HCl, and this time we are not using the sodium hydroxide, but we are using barium hydroxide, and it takes 27.4 milliliter of 0.0154 molar solution of barium hydroxide to completely neutralize the 20 ml of acid, that is HCl. So alright, let's start with what we know. The concentration of barium hydroxide is 0.015 molar, and we also know the molarity is equal to moles per liter. So if we want to calculate the number of moles, we need to calculate the volume of the alkali that have been used in liters, as 27.4 milliliter of the barium hydroxide have been used for the neutralization of 20 ml of HCl. So the volume is 0.0274 liter. So if we divide the molarity with the volume, we can calculate the number of moles of barium hydroxide. So in this way we get 0.000422 moles of barium hydroxide that has been used for the neutralization of the unknown concentration of HCl. Now let's write the neutralization reaction between HCl and barium hydroxide. So the barium hydroxide and HCl gives us products. Here we have 1 H plus ion in HCl and 2 hydroxyl ion in barium hydroxide that reacts to make water molecule, that is H2O. The other product that is formed from barium, that is 2 plus, and chloride having charge -1. So in order to have a neutral molecule of barium chloride, we need to have 2 chloride ions to make barium chloride neutral. So here we have barium chloride, other product. The next step is to balance the equation, and here we can see that the 2 hydrogens have been used from HCl in order to make 1 water molecule, and 2 chloride are used to make 1 barium chloride. So we need to multiply with 2 to HCl. So for neutralization reaction, 1 barium hydroxide unit is used to neutralize the acid of 2 units. Another thing we need to see that here we have 2 hydrogens, whereas in the left side we have 4 hydrogens. So we need to multiply with 2. So now we can see that everything is balanced on both sides of the equation. So for 1 moles of barium hydroxide, we need 2 moles of hydrochloric acid for the neutralization reaction. So here we already know that how many moles of barium hydroxide has been used to neutralize the unknown concentration of HCl, that is 0.000422 moles of barium hydroxide. It means that the solution of HCl have twice the concentration of the number of moles of barium hydroxide. Why? Because we can see from the balanced chemical equation that for each number of moles of barium hydroxide, 2 moles of HCl are used. So in this way we can figure out how many moles of HCl in the solution. So simply you can set up a proportion. So let's talk about the ratio between barium hydroxide and HCl, that is 1/2. Or more simple way to express the ratios, that is 1:2 between barium hydroxide and HCl. And if we know the concentration in terms of number of moles of barium hydroxide, that is given here, so how many moles of HCl can have? So we need to divide. That means we can calculate the number of moles of HCl by multiplying with 2. and we get 0.000844 moles of HCl. So these number of moles of HCl we have at equivalence point. So finally we just have to calculate the concentration of HCl by dividing the volume of HCl in ml. And as we know that the concentration of HCl is moles per liter, and we know the number of moles of HCl that are 0.000844, and the volume of the HCl that is used to neutralize the at equivalence point. So it's 20 ml, and if we convert this 20 ml into a milliliter, we need to change the volume into 0.020 liter. So in this way we can calculate the molarity of HCl, that is equal to 0.0422 molar, that is the concentration of our HCl. So let's see if we use the shortcut that is M1V1 is equal to N2V2, and according to the balanced chemical equation, N1 is equal to 2, that is the number of moles of HCl, and N2 is 1. And here we need to find the molarity of HCl, and we know the molarity of barium hydroxide, that is 0.0154 molar, and we need to multiply the volume, that is 27.4 milliliter of barium hydroxide over V1, that is the volume of HCl. So in this method we don't have need to change the volume into liters. So this shortcut must give the value of molarity of HCl directly, that is equal to 0.0411 molar.